Now let's look at the fourth and final point on the titration curve. Here we're going to consider the situation where you've added 50 milliliters of sodium hydroxide, and that will take you to what's called the equivalence point. All right, so point number 4. To find the pH, at this point in the titration curve, we once again begin by writing the list of major species. This is the same list of major species that we had in the last two videos. And once again, the hydroxide ion is going to react with the acetic acid to completion. So this is again a stoichiometry problem. So once again, we have to write the stoichiometry reaction and go through the stoichiometry limiting reactant problem by doing the before and after table. So I'm going to set that up on the next slide, and when we get to the next slide, that'll already be prepared for you. So as always, when we do stoichiometry problems and when we're doing one of these before, during, and after tables, you must find moles by multiplying molarity and volume. For the acetic acid, the volume of that solution was 50 milliliters, 0.05 liters. And the molarity of the acetic acid was 1 molar, so 1 mole per liter, 0.05 moles of acetic acid. For the sodium hydroxide, we now put in 50 milliliters of the 1 molar solution. So the volume of the sodium hydroxide solution was 50 milliliters, 0.05 liters. Molarity was 1 molar sodium hydroxide, and sodium hydroxide dissociates completely into hydroxide ion, so 1 mole per liter concentration for hydroxide ion. 0.05 moles of hydroxide ion, and no acetate ion initially. Now, as we've done before, you'll need to figure out which of these two is the limiting reactant. But interestingly here, you have a situation where you have an equal number of moles of the acetic acid and of the hydroxide ion. This is called the equivalence point, where the moles of the acid equals the moles of the hydroxide ion. And because you have an equal number of moles of each, all of the acid is going to react with all of the hydroxide ion. Both are the limiting reactant. Both completely wipe one another out. So all of the HA is used up. That goes to 0 because that's the limiting reactant. But also, the hydroxide ion goes to 0 because that's also the limiting reactant. Both are limiting here. Both completely wipe one another out. You're using up all 0.05 moles of the acetic acid and all 0.05 moles of the hydroxide ion. You produce 0.05 moles of acetate, so you're going to have 0.05 moles of acetate after the reaction goes to completion. With this in mind, let's think about what we should expect to get as a pH for this solution. I want you to think about what the major species are in this solution and make a prediction. Do you think that the pH at the equivalence point in this titration will be a number less than, equal to, or greater than 7? Take a moment to think this over and put in your answer. Having given you some time to work on this, let's talk about what the answer is here. Now, in order to make predictions of pH, it's really important to think about the major species that are present in your solution. So, let's write the list of major species that are remaining after that reaction goes to completion. We initially had acetic acid, Na+, hydroxide, and water. But in this reaction, all of the acetic acid was used up, so that's gone. We still have Na+, because that was just a spectator. The hydroxide ion was completely used up, so that's gone, that's off the list. We still have water present. And we made a new thing in doing the reaction. We produced the acetate ion, CH3COO-. From looking at this list of major species, what we see here is after that reaction goes to completion, what we have in our solution is the Na+ ion, which is a spectator. We have water, and we have the acetate ion, which is a weak base. So all that we have here essentially is a weak base in water. Therefore, we would expect that this solution should be basic. We predict a basic solution with a pH that should be greater than 7. So that's our answer there. Now let's think about how we're going to arrive at this answer. Looking at this list of major species that we have, I want you to think about whether or not we can just use the Henderson-Hasselbalch equation to find the pH at this point. So think this over. Can we use the Henderson-Hasselbalch equation to find the pH? Take a moment to put in your answer. All right, so in order to use the Henderson-Hasselbalch equation, you have to ask yourself, do you have a buffer? And what we see here is that the solution contains A minus, but we do not have any HA anymore because all of the acetic acid was consumed in the titration reaction or in that neutralization reaction. So we have A minus, but no HA. This is not a buffer, and so no Henderson-Hasselbalch equation for us here. So now that we've found that this is not a buffer and that you cannot use the Henderson-Hasselbalch equation, we have to think about how you're going to find the pH. What we can do is write the reaction that happens based on the major species that remain in your solution. Based on the list of major species that we have in our solution, the only two things that are eligible to react are the acetate ion and the water. So that's going to be our reaction. CH3 COO minus reacts with water, and because both are weak, this will be an equilibrium reaction, and the acetate ion acts as a base, so it gains a proton to become CH3COOH. The water, therefore, has to act as an acid, so it's going to donate a proton and become the hydroxide ion. Because both of these species are weak, and because this is an equilibrium reaction, we have to think about what equilibrium constant is controlling this reaction. What type of a K are we dealing with? Because we produce hydroxide ion, this is a Kb. And once we know the value of Kb, we can use that and we can set up an ice table in order to find what the pH of this solution is. And this is one of those situations where I'm kind of glad that I'm doing this lecture from home and not in Chem 1179, because in the past when I do this lecture and I say this part, that's when everyone starts groaning and they get like really upset. And now I don't have to hear anyone be upset when I say that. So let's now go through and make the ice table to find the pH for this solution. I'll remind you, as we begin setting up this ice table, that you must always, in an ice table, use units of concentration, or if it's a Kp, then you deal with pressures. But for K, Ka, Kb, Kw, these all deal with concentrations. And so that's the units that has to be used in your ice table. Do not attempt to use moles. The units don't just cancel out in the K expression, and so you have to be very careful about what you do. All right, so having set up the ice table, I'm now going to write out the Kb expression for this reaction. So Kb is the concentration of the acetic acid times the concentration of hydroxide. That's the number that I'm looking for to help me get the pH of the solution, over the concentration of the acetate ion. Notice in this expression, these are all concentrations, and the units don't all just like cancel out here, and so you have to make sure that you use concentration. So when the time comes for us to make the ice table, we have to convert the moles into molarity. And to do that, it's important to remember that molarity is equal to the number of moles over the volume. And so what you have to do is take moles and divide by the total volume of the solution. Right? Because when you did this titration, you added 50 milliliters of sodium hydroxide to 50 milliliters of acetic acid. That changes the volume of the solution, right? Like after you've mixed these two things together, you now have a solution with 100 milliliters of total volume. So you must use the 100 milliliters of total volume when you find the molarity of the acetate ion. To do that, we know from the before, during, and after table that the acetate ion was present at 0.05 moles. So we have 0.05 moles of the acetate ion. That was from the before, during, and after table. And then you divide by the total volume of solution, which is 100 milliliters or 0.1 liters. And so the initial concentration of the acetate ion is 0.5 molar. We don't care about water because it's not part of the K expression. And from the before, during, and after table, we determined that all of the acetic acid was used up. So there's initially none of that. And there's initially none of the hydroxide because that was also the limiting reactant that was also completely used up. Therefore, this reaction must proceed to the right. We're going to make some acetic acid, some hydroxide ion, and we're going to use up some of the acetate ion. Okay. I will point out that all of the values on this line were from the after line on the before, during, and after table. All right. Now, this reaction must proceed to the right. You're going to make some hydroxide, some acetic acid, and you're going to use up some of the acetate ion. Now, the value of K for this reaction is quite small, and so we'll be able to use the small x approximation, but to prove it to ourselves, we need the value of Kb anyway. Let's go ahead and calculate it. Kb comes from doing Kw over the Ka of the conjugate acid, so the Ka of acetic acid. The Kb, therefore, is equal to 10 to the minus 14 over the Ka of acetic acid is a given value. It's 1.8 times 10 to the minus 5. That gives us the value of Kb to be 5.6 times 10 to the minus 10. With this value of Kb being so small, you can go ahead and take the small x approximation and approximate the concentration of the acetate ion at equilibrium to be 0.5 molar. Now, we're going to take all of these values and plug them into the Kb expression. All right, Kb was 5.6 times 10 to the minus 10, and that's equal to the concentration of acetic acid at equilibrium, which was x, times the concentration of hydroxide at equilibrium, which was also x, over the concentration of the acetate ion at equilibrium, which was 0.5 molar. We'll go ahead and solve this for x. So if you solve for x, what you end up getting is that the value of x comes out to 1.67 times 10 to the minus 5. Then, whenever you find the value of x in a nice table, you must always think about what that value represents. So go back to the ICE table and look and see what x means. The ICE table is telling us that the value of x represents the concentration of hydroxide ion at equilibrium. So what we've found is the concentration of hydroxide ion. By taking a moment to think about that and to label this and to write it down, it prevents us from making a really big mistake, because it would really suck to go through this whole thing and get the wrong answer. When you go and take the negative log for this value, what you end up getting is not the pH, but the pOH, because this is the concentration of hydroxide. So the pOH would be the negative log of this value. And when you calculate that out, you find that the pOH is 4.77. And because you've labeled this, you know this is not the pH, this is the pOH, and so you know that you're not done. Additionally, at the outset, we had predicted that this solution should be basic because it contains a spectator, a weak base, and water. And so we should be getting a pH value that is greater than 7. So that's another way that we know that we're not done. It's another way that we avoid falling into a really common trap. So the last thing for us to do is to convert the pOH to a pH by using our relationship pH plus pOH equals 14. And so the pH is found by subtracting the pOH from 14. So 14 minus 4.77 is our pH, and that is 9.23. That is the pH at the equivalence point in this titration. Very important to go back and rework this example, and really to rework all of these titration examples, because as you go through and do these problems, you're getting more experience with solving acid-base problems. You're getting more experience with doing stoichiometry and limiting reactant problems. And in the case of the equivalence point, you're getting practice with a problem that involves both stoichiometry and equilibrium. One thing that's really important to keep in mind with regard to that is when you do the stoichiometry, you must use moles. When you do the equilibrium portion of the problem and you make an ice table, you must use concentration. And so you have to take any mole amounts that you have and divide them by the total volume of solution to get the concentration so that you can solve the problem correctly. One last thing that is helpful to do is to make sure that you're labeling all of your variables and making predictions as to what a reasonable answer is so that you don't fall into some of the common traps that happen in problems like this. All right, next what we're going to do is just kind of wrap up this section, summarize the results, and talk a little bit more about pH curves, as well as a review of the strategy for solving acid-base problems.